Okay, now we'll go into the 2015 to 16 semester 1 quiz 1. So for the first question on the analysis, so the first part they ask, is it okay if instead of comparing AI with the larger of its children in order to determine whether we want to swap two elements in a binary max heap, instead of that we do AI smaller than any of its children, right? So this is not going to work. So very easy counter example would be, let's say if we have a max heap, right? So in this case, if we do the swapping between AI with the larger of its children, we're going to get this, right? So this is the correct way, right? And this is a max heap. But if we swap with any one of the children, we're going to get this, which is not a max heap because your maximum element is 3 and it's not at the root, right? So obviously what Professor ABC is saying is wrong. Alright, so for the second question they ask, is there an AVL tree with 1000 vertices? 1000 vertices and a height of 30, right? And the answer is no, because the number of vertices that you have, or rather the height of your tree is going to be 2 smaller or equal to 2 times log 2n, right? Where n is the number of vertices, right? And the main reason for that is because of your balanced binary search tree structure of the entire AVL tree, right? So if we do this and we do something like log 2 of 1000, right? We realize that h cannot be, it's around, I think it's around 18. So it can definitely not be 30. So this is false as well. For question 3, they ask whether union by rank and path compression is important and whether we can still achieve O1 performance, roughly constant performance, if we are only dealing with up to 1 million items. So this is not true, because if we have 1 million items, remember that it is possible in the worst case scenario to have 0, 1, 2, all the way to, let's say this 999, 999, right? So 1 million elements all in one row. And so if in this case, if we want to do find set of 0, we have to keep traversing this, and it's going to take 1 million operations, which is obviously not O1, right? It is really On, where n is the number of elements. In this case 1 million elements, right? So this is also false. Okay, so question 4. So they ask whether it's possible to have efficient bit manipulations of 10,000 booleans. 10,000 booleans, right? And the answer is no. And the main reason is that if we look at our current computer organization, so each integer has a maximum of 64 bits, right? So you can think of 64 bits as 64 booleans, right? Which is because if these are your 64 bits, right? Each can be a 0 or 1, 0 or 1, 0 or 1, and so on, right? So you can think of it as 64 booleans, right? And that is definitely much less than 10,000 booleans. So your bit operations can be done in O1, right? If you only have 64 booleans, you can just use one integer to do all your bit manipulations. But if you want 10,000 booleans, then you need an array of booleans, which is not going to be in O1, right? So this is not possible to do 10,000 boolean bit manipulation operations in O1. And the last question, question number 5, they ask an adjacency matrix representation M of a graph G is symmetrical. So M is equals to M transpose. So they ask is if the graph G is an undirected graph. So as we mentioned just now, if your adjacency matrix is symmetrical, right, for instance something like this, symmetrical, right? 0, 1, 2, 0, 1, 2. Right, you realize that what this is going to say is 0 is connected to 1, right? And 0 is connected to 2. At the same time, 1 is connected to 0, and 2 is connected to 0, right? You can see here that it's really an undirected graph. So as long as the property is held that it's symmetrical along this line, meaning that M equals to M transpose, then the graph is an undirected graph. Alright, okay.